Okay, welcome to Math 150, Section 1, lecture 28 or so. So what I want to do today is I want to talk a little bit more about Taylor series, and I want to talk about some of the applications. So why do we care so much about Taylor series? Well, it's really hard to study anything that's not straight line. And so one of the great things about Taylor series is, the first order Taylor series is you convert something to a straight line. You can actually do a little bit better. Rather than converting something to a straight line, you can convert it to parabola, or cubic, etc. The higher the degree you look at, the more complicated, the more involved it is, but the better approximation you can do. And the hope is that when you look at these Taylor series, that it will converge, and not only will it converge, that it will converge to the original function. Sadly, it is possible for the Taylor series to converge to something other than the original function. We saw that with the terrible example of e to the negative 1 over x squared. But most of the time, things will be fine. Most of the time, for a good function, the Taylor series will converge to it. And you can even describe how rapidly it converges. So the argument in the notes that I gave you, this is not the best result in terms of how quickly they converge. It is a very easy argument to make in terms of how much algebra do I need to do, how much do I need to assume about the functions, and I would rather trade off a little bit on a cleaner proof than a better result at the cost of more analysis. You can get a higher factorial in the denominator. So when we proved the fundamental theorem of calculus, what was the result we kept going to again and again and again? What was the go-to result? The lecture was titled The One with the Mean Value Theorem. So the mean value theorem is extremely important in all of these arguments. And it basically says, let's say f is continuous and differentiable on AB, then there exists a C in AB. So the sign like that means there exists a C such that f prime of C is f of B minus f of A over B minus A. And if this is A and this is B, the average speed from A to B is just the slope of that line. And the mean value theorem tells us that there must be at least one point where the instantaneous speed equals the average speed. For this example, it turns out that there would be two choose. And maybe we'll choose that to be the value of C that we care about. So we talked before about why the mean value theorem is true. Absolutely beautiful result. If you want, we can rewrite things as f of B is f of A plus f prime of C B minus A. Or if we let B equals X, and maybe let A equals 0, f of X is f of 0 plus f prime of C times X. So this is exact. There's no error here. What is your concern about this? Why is this not the greatest theorem of all time? What could be better? So there is some C between A and B such that f of X is f of 0, where you start, plus the speed at time C times how much time has elapsed X. What could be better? Well, but this is already perfect. So if I did a different point other than B, I would just get a different point C here. What might you want to know? This is exact, but I don't know where C is. Right? Imagine you're a consultant for a presidential campaign. You say, good news, you have a path to 270 electoral votes. Wonderful, and what is that path will have? It's a theoretical argument. It's nice to know that the path exists, but you want to know, well, what is it? And so here, the drawback of the mean value thing is we don't know where that point C is. We just know that there is a C between A and B. For many things, that's enough. And when we proved the fundamental theorem of calculus, we didn't need to know precisely where that point was. And this is a really nice point of theoretical mathematics. For a lot of arguments, you just need to know something exists. You just need to know a few properties of it. You don't need to know every little thing about it, such as its location. It would be nice to know its location. And so instead, we often use the Taylor series. So the nth order Taylor series of f would be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared all the way up to the nth derivative at 0 over n factorial x to the n. So that would be the nth order Taylor series. And if you check the derivatives up to the nth order on the right-hand side, match the derivatives of f at 0 for the first n. So the derivatives are set to match up. And then the question becomes, how close is it? So you want to estimate the error. So the error would be the absolute value of f of x minus t n f of x. So you want to know how big is that? The hope is, as n gets larger and larger and larger, that error should get smaller and smaller and smaller. And for many functions, that's the case. And the question is just how quickly. So what I want to do is I want to just quickly sketch how you would do these estimates. How would you estimate what the error is? And so very similar to the proof of the fundamental theorem of calculus, this is also a lecture that could be titled The One with the Mean Value Theorem, the sequel. And when in doubt, apply the mean value theorem and keep applying, keep applying, keep applying. The mean value theorem is in some sense, a poor mathematician's Taylor series. It's not quite the first order Taylor series. The first order Taylor series would have an f prime of 0. We have instead an f prime of c. Yes? C is a function of x. So if you want, C is really a function of x or a function of b. This is what's going on at one specific point. And so sometimes we actually would write C sub x or C sub b or C sub ab to indicate what C depends on. And you're absolutely right that it's good to have explicit notation so that you don't accidentally think that this is true for all values of x. This is the very special case when b equals x and a equals 0.
Can you perform that in the Taylor series? So that's what you're going to
So this is perfect at one specific point, but we don't know what that C is. So when I want to try to approximate my function, I need to know, well, what does that C if I want to use this approximation? Here, I'm explicitly telling you, if you want to look at an approximation with a line, a parabola, a cubic, etc., you tell me the degree, I will tell you, here's a really good polynomial to use. And it's explicit, and all of the constants, all the coefficients of the polynomial are coming from values of the derivative. So it gives me a really nice recipe. Over here, if I want to use this to discuss my function, it's exact, but I don't know where that point C is. Okay, so let's let h of x equal f of x minus the nth Taylor series at x. Well, that's essentially the error. This is the error function. And we want to estimate how large is h of x. I claim there's one value of x where it should be very easy to evaluate the size of h of x. Anybody know what that one value of x would be? So what value of x would it be very easy to evaluate this difference? 0. And so if we look at h of 0, that's f of 0 minus the Taylor series. Well, if I put in 0 for x, the Taylor series is just f of 0. So this is just equal to 0. So we know it's perfectly exact at 0. Well, that's not surprising. We've rigged it to be that. And now, let's see how accurate it is a little bit of ways. So we want to estimate h of x. And the trick is if I want to study h of x, what are the two algebraic things we can do in mathematics that don't change an expression? Multiply by 1 and add 0. Anybody have a suggestion of what would be a good 0 to either add or subtract? So I want something that's 0 that's related to h. Yeah, so let's subtract out h of 0. And then by the mean value theorem, this is h prime at some point, let's call it c1 times x minus 0. And so c1 lives in the interval 0. I'll assume here that x is positive and not negative. If x was negative, it would be simple. So by the mean value theorem, this is just h of x minus h of 0 over x minus 0 is h prime of c1. Okay, let's continue. H prime of x is going to be f prime of x minus, I have the derivative of the Taylor series. Right? So the question is just how much detail to go through. I'll write it out like this. When I take the derivative, I'm going to get f prime of 0. Then I'll have f double prime of 0 with 2 factorial. The derivative of x squared is 2x. So it'll be 2f double prime of 0 over 2 factorial x plus all the way up to n. The nth derivative at 0 over n factorial x to the n minus 1. What's h prime of 0? So what would you get when you put in 0? 0. Everything from f double prime onward vanishes because it still has an x. And you'll just get f prime of 0 minus f prime of 0. So if we want to understand how large is h prime of c1, h prime of c1 is equal to h prime of c1 minus h prime of 0, right? I've just subtracted 0. And what does that equal? By the mean value theorem, it's going to be h double prime of some c2 times c1 minus 0 times x minus 0. And now we do shampoo mathematics. What are the instructions on shampoo? Lather, rinse, repeat. Right? Does it mean you only repeat once or you keep doing it indefinitely?
Well, every day.
It's a little unclear. Do you get stuck in this infinite cycle, lather, rinse, repeat, lather, rinse, repeat, lather, rinse, repeat? Or is it lather, rinse, and then repeat once more? We just keep doing this. How many times do you think we keep doing this? When do we stop? I'm sorry? Well, we don't know. They may not be getting small. C1 might be extremely close to x, and C2 might be extremely close to C1, which is close to x. But we know Tn of f is a polynomial of degree n. If we do this n times, we get the nth derivative at 0. If we do it n plus 1 times, there's nothing left over. And so we can keep doing this, and we eventually get it equals the n plus first derivative at some point Cn plus 1, and then you'll have Cn minus 1 all the way down to x. And so if we want to get a sense of how large can this be, so the absolute value of the error is going to be less than or equal to the maximum value over, say, Cn plus 1 less than or equal to x of the n plus first derivative at Cn plus 1 times x, I think I get it to the n plus first power. So double check and make sure I have not made an algebra mistake in terms of marching down. Yep, great. Which middle part, right here? I'm taking the maximum value of Cn plus 1 as it ranges between minus x and x. And I'm evaluating the n plus first derivative of that. So we keep doing this n plus 1 times. And when we finish, the question is how large can the error be when we finish? Well, let's look at the worst possible case. Let's look and see where's the n plus first derivative largest. And if the n plus first derivative is bounded, if x is very small, this is going to be a small number to the n plus first power. And so then the error is going to be very small. With more work, we could actually have, I believe, like an n plus 1 factorial down below, which really makes this small and really shows you how well it converges. But this is a nice application of just constantly using mean value thing, mean value thing, mean value thing. If you want as a nice exercise, explicitly do the calculation when you take n equals 1 or 2, and just go through all the details. And I'm just saying, let's just use the worst possible value, the largest possible value that the n plus first derivative can be. And then for all the c's, each c is less than the previous one. So the worst case is they're all essentially the size of x. So the error can't be larger than this. So this is a quick proof of how the Taylor series converges. And so again, if the n plus first derivative is not too large, let's say I have something like cosine or sine. Well, cosine and sine and all their derivatives are bounded by 1 in absolute value. So this number won't be that large. And so if I take x to be 1/10, then this is going to be extremely small when it is large. And again, this is not the best result possible, but it's a good result without too much work. And so this is Taylor's theorem with remainder. Not the best remainder, but a decent remainder. Yes? Well, we've never changed it. We have h of x equals h prime of c1 times x. And then h prime of c1 is h double prime of c2 times c1x. So the equality keeps going. H of x is equal to this, is equal to this, is equal to this, is all the way equal to this. So it's still equal. And now what I'm doing is I'm replacing this with potentially something a little bit larger. And I'm taking the c's and I'm replacing them with something that's potentially a little bit larger. I'm saying, what's the worst possible case? In practice, it's probably not going to be this bad. But for the purposes of analysis, you always assume the worst thing. Okay, so this is a big theorem. It's nice to see a few of these during the semester. And this also allows us to review some of the material from earlier in the semester. It allows us to review some of the derivatives. It allows us to review the value theorem. It allows us to review what it means for a function to be bounded. So this is a really good problem in terms of review. Okay. Any questions about this. So I want to shift now to the birthday problem. Given the number of people we have, I'm not going to play the birthday problem live. We could play the problem with months. And so do we think that there are at least 2 people who were born in the same month in this classroom right now? I think it's extremely likely. We have 6 people here. We've got a couple more watching this through Zoom. I would be shocked if we didn't have at least 1 kid that had the same month. The question becomes, how many people do you need to have at least a 50% chance that 2 people share a birthday? One of the things that's extremely important about problems is making sure you clearly state what you are doing. And I have learned the hard way that even if you state what you are doing, people do not always read all the assumptions you put there and can take your work in other ways. What might we be assuming when we're trying to analyze the distribution of birthdays and trying to understand the probability that 2 people share a birthday? What might you be assuming? Every day has an equal likelihood. Do you think that's true? Why not? Delicately, please. So there are certain times of the year where people are more likely. Now, it would be fascinating, does that correlate with intelligence? It does correlate with athletic ability, or maybe shall we say athletic performance. Anybody know why birth dates might correlate with athletic performance? Malcolm Gladwell has a wonderful passage on this. Yes? Yes. So when you're younger, do you want to just make the cut as being old enough to play, or do you want to just miss? You want to just miss, because then you will be one of the oldest kids left. And when you're really young, those few months to a year is huge percentage-wise. And so you're often a little bit bigger. And so if you're a little bit bigger, that's a competitive advantage. So you look like a better player. So you get more playing time, you get invited to other things, and it just propagates up and up and up. And Malcolm Gladwell has a wonderful passage in his book, Outliers, where he takes the junior hockey championship game in Canada from some year and replaces the names of the players with their birthdays. And it's essentially January, February, and March just passing amongst each other, shooting against a goal defended by January, February, March, with a sprinkling of maybe some Aprils and Mays. Which is fascinating when you think about it, that you're almost surely hockey talent is not confined to people born in those months, but we have a system that is promoting the people born in those months over others. And so you are losing out on a huge amount of talent by creating a structure where small little differences in the beginning are allowed to fester and grow. There are a lot of conversations going on about biases and whatnot. This is, to me, a terrific example of how, through no fault of your own, certain people are not getting the same opportunity. I have identical twins in my family. Last year, I actually had identical twins taking multivariable calculus together. Anyway, I still did the birthday problem. I was not really worried with identical twins. It is possible. It does occasionally happen where identical twins are not born on the same day, but it's very rare. So we will assume all days are equally likely. There's something else that I'm going to assume just for the interest of the calculation. There's something you have to worry a little bit about. Somebody might argue that all days are not equally likely. What day might they worry about? February 28th? February 29th. So I have a rule with admissions that no one is allowed to take my class if they were born on February 29th. And just because of the way things are, this is of course a joke. If you're born on February 29th, you are welcome to take the class. But February 29th comes around once every 4 years. And so what do you do for people born on that day? So we will assume 365 days in the year. And we want to calculate what is the probability that if I assume birthdays are randomly selected and each person's birthday is independent of everyone else's, that I have at least two people who share a birthday. Frequently in mathematics, rather than analyzing the probability that something happens, what might be easier? Subtract it from one. Find the probability that something doesn't happen. One of the difficulties is maybe we have 3 people born on the same day. Maybe we have multiple pairs of 2. There's a lot of different ways to have at least 2 people sharing a birthday. It's much easier to look at the probability that no one shares a birthday and see when is that 50%. And when that's 50%, then the probability that you have at least 2 people who share a birthday is going to also be 50%. So next semester, I will probably be teaching probability math 341. While you technically should have linear algebra as a prereq, this is a pre-core 300 level math class, and it's a nice class on applications. So let's try to calculate Pn equals probability n people know to share a birthday. We can do it for Earth, or we can do it for any planet by just saying that there are D days in the year. Are people okay doing D days in the year, and then we can just do a search and replace, or specialize D to 365? On Pluto, which sadly is no longer considered a planet, I think there's around 9,000 days in Plutonian year. So we'll assume D days. So can somebody give me just a rough upper bound of how many people you need before you're guaranteed that at least 2 people share a birthday? If you have this many people, you know at least 2 will share a birthday. Yeah, once you have D plus 1, you're safe. Is it possible with D people that you don't share a birthday? Yes, but it's extremely unlikely. Even if you had D over 2 people, when you think about it, the last person who comes in, if everybody didn't have a birthday in common, when that last person comes in, there's already a 50% chance that they would have given you a matched birthday. And the person right before them also would have been very close to 50%, and the person before that already very close to 50%. So I would say a quick estimate would tell us we think it's much less than D over 2. Because by D over 2, each person is already giving you roughly 50%. So what if we had only 1 person? What's the probability if you have 1 person that nobody shares a birthday? 100%. I'm going to write that as 1 minus 0 over D. Now the next person walks in. What's the probability the next person doesn't share a birthday with the first person? So the first person, I didn't have to worry about any days. The second person, how many days do I have to worry about? 1. So it would be 1 minus 1 over D. And now the next person walks in. How many days must they avoid? 2. So it would be 1 minus 2 over D. And this continues until I get to the last one. And for the last person, how many days do I have to avoid? Well, we have n people know 2 share a birthday. It's what? Okay. Not D minus 1. We have n people walking in. N minus 1. So very good to remember that it's not n, it's n minus 1. Okay, so we have to understand this product. Anybody have any thoughts as to how we might understand this product?
No.
Logs, right? Whenever you see a product, thou shalt take a logarithm. If you are volunteering in the elementary school and somebody's having trouble multiplying 3 times 4, okay, don't take a logarithm then. Almost any other time in a higher level math course, think about taking a logarithm. And you want this to be approximately 1. So we would want the log of Pn is going to be the sum, k goes from 0 to n minus 1, the log of 1 minus k over d. Because the log of a product is the sum of the logs. And now, all of a sudden, we have converted a problem that is terrifying. If you wanted to try to multiply this out with equals 365, you would have 1 times 364 over 365 times 363 over 365 times 362 over 365, and you would keep multiplying like that until you got to a half. And so you might have 365 dot 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 all the way down to 365 minus n minus 1 all over 365 to the n. You could write this as 365 factorial over 365 minus n factorial times 365 to the n. If you try to compute this directly on your calculator, it will almost surely explode. Or, actually not explode, it will almost surely say your error cannot compute, that you'll have an overflow when the calculator tries to do something like 365 factorial. The way you can get around that is you keep doing it term by term. 364 over 365 times 363 over 365 times 362 over 365, and you keep doing that until you get 1/2. If I try to do this directly, the number becomes so large. Okay, so now what we want to do is we want to try to understand the log of 1 minus k over d. And so we proved earlier the log of 1 minus x is negative x minus x squared over 2 minus x cubed over 3. But this was the Taylor series of the log of 1 minus x. So that was the one example that I did explicitly in class. Is we calculated, let's let f of x equal log of 1 minus x. Let's calculate f prime, f double prime, f triple prime, and so on and so on and so on. This was not a random choice as to why I chose to compute the log of 1 minus x versus the log of 1 plus x other functions. I knew I wanted to get to the birthday problem later in the semester, so I wanted to spend the time calculating that. If x is small, the log of 1 minus x is approximately what? It's approximately negative x. You could get a better estimate if you kept the x squared term, but if x is pretty small, it's not a bad approximation. So what I can do is I can say the log of Pn is approximately negative the sum k goes from 0 to n minus 1 k over d, or negative 1 over d, the sum k goes from 0 to n minus 1 over k. That's a sum we've evaluated before. And we can use the Gauss trick to evaluate it. So we have 0 plus 1 plus 2 plus m. I'm going to just do the more general case. And I can write the numbers backwards. M plus n minus 1 plus 0. And if I add, what's 0 plus m? M. What's 1 plus m minus 1? So all of these are m. And how many copies do we have? Well, how many times do we have m? M plus 1, because we started at 0. So m plus 1 times. We get the sum, k goes from 0 to m of k is equal to m times n plus 1 over 2. I have to divide by 2 because I've doubled this. I've counted every number twice. So that means for us, the log of Pn is approximately negative 1 over d n minus 1 times n over 2. We want to solve for n. And this is basically the log of 1/2, which is negative log 2. We're using another log. The log of 2 to the negative 1 is negative 1 log 2. Okay, so we get n minus 1 times n, the minus signs cancel, equals 2d log 2. How would we solve this? What could we do? How could we solve this? What are we trying to find? We want to find n, so find n. What kind of equation is this? It's a quadratic. How do you solve a quadratic? You could use the quadratic formula. Rather than using the quadratic formula, instead what I'm going to do is say, well, look, n minus 1 times n, that's approximately n minus 1/2 squared. If I expand it, this is n squared minus n. If I expand so, this is n squared minus n plus a 4. I could use the quadratic formula, but I'm already doing some approximations. Let me just do it like this, so it's a little bit easier. So n minus 1/2 squared is approximately 2d log 2. I'm going to write that as d log 4. I'm going to move the 2 inside. Well, if n minus 1/2 squared is about d log 4, that means n is approximately 1/2 plus the square root of d log 4. Take the square root of both sides and then add it back. And so just to give you a sense here, I'm using Mathematica. Mathematica can handle large numbers. If I give it 365 factorial, I'm asking what is 365 factorial? It's about 10 to the 778. So if you want to just calculate 365 factorial, it's going to be huge. That will almost surely overflow your calculator. We want to estimate 1/2 plus the square root of d log 4. So if I let create a define function, so it'll be 0.5 plus the square root of d log 4. I think I can actually use capital D in Mathematica. What do you think capital D means in Mathematica? Differentiation, so I'll use a lowercase d. So if I do 365, it gives me as an answer 22.9944. So you would need around 23 people. And you can now see why it probably doesn't really matter if I'm replacing this with an n minus 1/2. We're not going to allow 3/4 of a person to come into a party. Right? We're looking for the nearest integer. And so if you wanted to, we could solve. So it's going to be n times n minus 1 minus d is going to be 365 log of 4 equals 0, and solve this for n. And so Mathematica gives answers as negative 21.99. Okay, negative 22 people is unreasonable. And the other answer gives us 22.9999. So if I didn't do this approximation, instead of getting 22.9944, I get 22.9999. It's really interesting how close this is to being an integer. What's wonderful about this is that you can see how things change as you change d. It's growing proportional to the square root of d. So if you move to Pluto, with around 90,000 days in the year, then you know it's going to be on the order of square root of 90,000. Right? Anybody know roughly what the square root of 90,000 is? Yeah, so this is the same thing as the square root of 9, square root of 10,000. So it would be 3 times 100. So that would be 300. I want the log of 4 base e. Well, the log of e is going to be 1. The log of e squared is 2. This is somewhere between 1 and 2. So, I can quickly estimate, call it 1.5 times 300, call it 450. Just as a quick rough estimate. And the actual answer would be 90,000. Would be 353. Okay, so the log of 4, you're estimating that as 1.5 is not a great estimate, but not horrible. So this is the birthday problem. It is a really nice way to tie together a lot of the things we're doing. So we look at sums like this when we were doing the tests of the fundamental theorem of calculus. If the fundamental theorem of calculus can only find areas under straight lines, the rectangle, the triangle, it's not really that exciting. When we start doing parabolas and cubics, we start getting things we hadn't seen before. And that was a real accomplishment. This is a very nice trick that works because we have everything to the first power. If I give you more general cases, if I look at sums of squares, sums of cubes, sums of fourth powers, the argument is harder, but there are explicit formulas. We then find a product, and the way we handle the product is we use our idea that, well, whenever you have a product, consider taking a log. A log of a product is the sum of the logs. And now we use Taylor series to approximate. What you can do as a nice exercise is keep the next term, keep the x squared term. If you do that, you will also have a sum of k squared. And we do have a formula for that. The sum k goes from 0 to n of k squared is k plus 1, 2k plus 1 over 6. And as a quick check, if k equals 3, 1 squared plus 2 squared plus 3 squared, 9, 10, 14. So that would be 3 times 4 times 7 is 6. Good, and that would be 14. So the sum, oh, I'm sorry, this is not k, it should be n's. And so this is a formula for the sum of squares. And so if you felt that this wasn't a great approximation, you could actually keep the next term and you'd have a more involved expression to solve. Rather than having a quadratic now, you would now have a cubic. Okay, cubic is not pleasant, but there is an explicit formula for the cubic. There are ways to approximate roots of cubics, and we have Newton's methods. So we have ways that we could solve it. How else could you try to do this? How else could you try to estimate the sum of the log of 1 minus k over d? There's one other thing we could do from a unit on sequences and series. As k gets larger, what happens to the log of 1 minus k over d? What happens to 1 minus k over d? Does it get larger, smaller, or does it alternate? If k increases, what happens to 1 minus k over d? It's getting smaller. What happens to the log of 1 minus k over d? Yes, you're getting more and more negative. So you have something that's moving in one direction. How might you try to approximate this? Yeah, try the integral test. So try converting this to an integral and try to use the integral test to estimate the value of that sum. So as an extra credit problem, try to use the integral test to attack this. This is a great problem for the end of the semester to just show all the different stuff that we're doing coming together. Okay, any other questions on the birthday problem? It would be interesting to look at the distribution of birthdays at Williams in terms of, do you think it makes a difference for people for their academic development if they just make or just miss the cutoff for schools? There are a lot of families that deliberately hold kids back a year. That you could have just made it, but they don't want their kid to be one of the youngest. This is especially true by some families where they might be concerned about what would happen with the kids playing athletics. If you're one of the smaller kids in the grade, a lot of times it's a maturity issue. But it might be interesting to see, is there some kind of bias in the distribution of birthdays among Williams students? And is academic performance related to just where we have the cutoff in that our school year starts strangely in most places in September, maybe end of August in a couple of places. All right, this is a good place to stop.